Well, we're happy to have Bradley Dirks, who's going to talk about microlocalization and journal linear combinations.
Yeah, thanks so much. Okay, yeah, so I'll just talk about the goal. So I'd like to introduce some math, which has recently appeared in my work. So it's the title of the talk. But I guess I'll say what I work on. So I like to think about singularities in complex algebraic geometry. So D modules are the usual tool I use to study these singularities, and specifically Hodge modules, which are some enhancement of D modules. So yeah, if you're interested in these topics, please come talk to me at any point. Okay, so I'll start out a little bit basic. So if you have a topological space, you can look at local systems on that topological space. So these are just locally constant sheaves of C vector spaces. I'm always going to think about a connected complex manifold. Really, I want it to be like a smooth algebraic variety, but for now, we'll work in the analytic category. And these local systems, if you tensor with the holomorphic functions, that's what this little operation is, allows you to think about them in terms of like holomorphic flat connections of like on vector bundle. As if you know, like a connection is some way to differentiate the sections of your vector bundle. So maybe it shouldn't come as a surprise that basically these flat connections are certain modules over the ring of differential operators. So basically the flatness allows you to extend these differentiation actions to the entire ring. So I basically say the commutativity holds between different partial derivatives. So if you haven't seen differential operators before, just think of them as local sums of holomorphic coefficients on some dx to the alphas. And like I said, I really want to think about algebraic varieties. So we're going to think about dx modules on smooth algebraic varieties. So I guess now holomorphic will mean polynomial or algebraic or regular function. Also, there is some color scheme in this slide, but it will not be, what's the word, consistent throughout all of them. Don't pay too close attention. I just didn't want you to get bored looking at black text the whole time. Yeah. So this leads to some very deep math called the Riemann-Hilbert correspondence. So I'm going to start with some smooth, complex algebraic variety, connected. So work of Deline and Kachivar and Mebku led to this correspondence, which is enhancing a classical story, which I already gave on, I guess, the second slide. So certain flat connections correspond to local system in some bijective way. But really, we want to look at local systems on the analytic manifold, just because then you have interesting topology. So yeah, I mentioned that they sit inside some nice category of D modules, because you can differentiate sections. And the question is, can you fill in what do local systems sit inside? So we can think of dx modules as some algebraic objects, although really you might think that they have more of a topological flavor because this has an answer, and the answer is perverse sheaves, which I'm not going to define. But all I really want to stress in this slide is that there's two sides to this story, sort of the D module side and the topological side. And certain constructions are easier in the D module category. And certain ones are easier in the topological category. So I'll present you one which is probably easier in the topological category, but we're going to do it in the D module world. So if you have a closed embedding from some closed subvariety into your smooth complex algebraic variety, you want to ask, how can you restrict M to a D module on Z? Really, I always want to talk about D modules on a smooth variety so that I have this local coordinate description. So I want to compute I lower star, I upper star. So I push it back forward to X and try to think about this object. You run into an issue, which is that is not just a single D module in general. It's a complex of D modules. So it lives in the derived category. So let's just first look at the hypersurface case. So now you've chosen some local defining equation. Oh, and here's my cartoon of a hypersurface. It's a blob with a line in it. Now this restriction is a two-term complex. So it's represented by these words, which you might have heard before. So nearby and vanishing cycles. There's a canonical morphism between them. So it's called can. I'll just mention the construction of nearby and vanishing cycles is easier in the topological category. Although I always like to live in the D module world. So if you ask me, I prefer the D module way. Okay, but actually this, like, writing it in this way leads to refined data. So these nearby and vanishing cycles, they're actually part of some larger sheaf or D module, which has various eigenvalues. So those lambdas you can think of as eigenvalues or logarithms of eigenvalues. And the ones where lambda is not equal to 1 didn't show up in this formula at all. So they sort of have extra information beyond the restriction of the D module. I mean, even lambda equals 1, like their individual pieces sitting on their own have more information than this complex. So you can think about them. They do end up still being nice. So they stay in this category where you have this correspondence. They're supported on the hypersurface. And yeah, so I would think of this as some refined data for your D module trying to restrict to your hypersurface. And in fact, they carry a lot of singularity information. So even, well, okay, in this specific example, you let your D module be the trivial one, so OX. If these vanishing cycles are 0, so the ones with eigenvalue 1, that implies that your hypersurface satisfies Poincare duality. So like this condition is essentially equivalent, because my ambient variety is smooth, to saying that the hypersurface is rationally smooth. So basically it has Poincare duality. So already you can expect it's pretty hard to compute these things. They carry up so much data. But yeah, I'd like to move on from the hypersurface case to a higher codimension case. So let's take some subvariety defined by several polynomials or regular functions, and we're still inside X. So X will always be smooth. I always work in some smooth ambient space. You can associate to a dx module various dz modules, mz lambda, where lambda is in Q, or R, because I guess I didn't put any quasi-unipotence hypothesis. They will still allow you to compute the restriction. Now it's actually, it has R plus 1 terms, so like between negative R and 0. It's a causal complex instead of just a single morphism. But these are not nice. So these modules do not even need to be coherent over dx. So they're very bad in some, I mean, they're coherent over a larger ring, but they don't fit very well into the story. And especially like you can't try to apply going backwards in the perverse construction. Actually, it's not so bad. You just bundle them all together and you do get a nice object. If you take the direct sum over all the lambdas, there's basically a discrete set over which these things are non-zero. You get what's called the Verdier specialization. This is a nice D module, but now it will sit on the normal bundle. And I guess, right, so the normal bundle will probably be singular. So you should think of that sitting inside of like X cross A to the R, where R was your number of defining equations. Okay, the solutions seem to be bundle together all of your refined restriction data, and you do get a nice module. This is called specialization. This is like the first step in the first word in my title, which is microlocalization. The second step is the Fourier Laplace transform. So I take some trivial bundle over X, and I call the coordinates on the fibers Z, and I take its dual trivial bundle, which is still trivial, and I call those coordinates Y, so the dual coordinates are Y. If I start with a DE module, I can construct a DE dual module, which is called the Fourier Laplace transform, essentially by following the rules of the Fourier Laplace transform from differential equations or wherever you've seen this. So you keep the dx action. So operators coming from X act in the same exact way, but now you just formally say yi acts by negative dzi and dyi acts by zi. Very easy to write down. Doesn't preserve this nice property, and so you kind of would struggle to write down the formula in the perverse setting. There is one if you put extra adjectives in front of your objects, but I don't really want to talk about that. But here's this idea where there's two sides to the story. And in the D module world, I could define almost trivially some new operation, which is kind of hard to cook up in the perverse setting. Okay, but it turns out that if you do this specialization construction, that is a D module where when you Fourier transform, it remains nice. So it stays in this nice category. And you call that the microlocalization along Z. Well, I guess you can call it a microlocalization because there's several notions floating around in D module theory. And it's denoted by mu, I guess, for n. Okay, so this is the first word in my talk. This gives you a module on this dual trivial bundle with the coordinates y. But you can construct another module on that dual bundle. So you take G, this is where the word general linear combination comes in. You take a general, and so general that you haven't even specified what the yi's are yet. A general linear combination of your defining equations. If you formally adjoin the variables y to your D module, you can do this just because the y's are independent of the x variables. This is also just the D module pullback up to some shift. You can then take the vanishing cycles along this hypersurface G. Okay, so you might argue this is maybe an easier construction because you did a simple pullback and then you did something which you know lives in the nice world. And I guess in general, people believe that, I don't know, nearby and vanishing cycles for hypersurfaces are easier to understand than those n lambda z's that I wrote down earlier. Great. So one theorem of Shenyu Chen, myself, Mircea Mustatsa, and Sebastian Olano is if you take the trivial D module, you actually have a natural isomorphism between these two constructions. So I wrote O of Y, I should have wrote O of E dual, but you just adjoin the polynomial variables to O of X. What we really showed was a filtered version of this, where this is the associated graded of that filtered version. So we were able to prove sort of a better thing than this theorem. We applied this to the study of singularities, specifically trying to like enumerate how bad a singularity is. This is something called the minimal exponent. So if you saw my AG seminar talk, it was about that. Later, I mean, this is not really different from that. You can just run the same argument with any nice D module. And I guess in both of these, we really wanted to keep track of the Hodge and the weight filtration. So if you care about like Hodge modules, all of these operations will preserve this category. And so you might ask, like, how do the Hodge and weight filtrations behave on both sides? And they're the same. And recently I applied this to the radon transform. So there's some famous comparison of Fourier-Laplace transform and radon transform. And I was able to use this sort of last theorem to prove that in the mixed Hodge module setting. Okay, but there are some questions because this is in the D module world, but all those constructions are possible in the perverse sheaf world. So Kendrick-Scheffers actually showed that there is a comparison isomorphism. I mean, so I'm heavily simplifying the theorem of Kendrick-Scheffers, but at least one part of this paper of his is that there is a comparison isomorphism similar to the one on the last page in this perverse category. So a natural question is, are they compatible, right? We have two sides of the same story. Does the isomorphism that we have agree with this one that Scheffers has constructed? I don't know the answer to that. It would be interesting. And an interesting way to answer this would be, what if we can just do it all with like functors and geometry? So, I mean, I don't know about motivic things, but I would call this maybe a motivic argument where you're just using geometry and duality and push forward, pull back, and nearby and vanishing cycles. I don't know the answer to either of these, but I think because isomorphisms exist on both sides, perhaps we can realize them in some nice functorial way. Okay, yeah, thank you so much.
Any much questions?
Financial meaning autonomic with regular
Yeah, that's it. And I guess probably the word quasi-unipotent I want to float around everyone, but yeah. Yeah.
Can you say again in your last slide what the word geometry means?
Oh, yeah, I just mean like if you can write out like certain diagrams of morphisms between varieties so that these isomorphisms are realized by, I don't know, base changing various push forwards and pullbacks and dualities and things like this, yeah. And really 6 functors is probably the only word you need to see here. And then geometry is just to talk about pushing forward and pulling back.
Okay.
In the higher codimension case, do these M lambdas have some concrete interpretation like the homology of the Milnor fiber?
So this specialization is related to the cohomology of the Milnor fiber in the like isolated complete intersection here. So you kind of still want to bundle them all together. Yeah, the individual pieces themselves are sort of hard to like put into the theory. And it's always, well, I feel it's better to think about the bundle, like the specialization as a whole.
So you were speaking of complete intersection, but do you need the actual equation or just the ideal?
Oh, yeah, so these constructions like do not depend on the chosen generator. But I get like to really, I mean, like, okay. okay, I should say like they will hold no matter what generators you choose. I guess clearly like here, like G depends on the generator.
What sort of things about singularities can it prove?
Yeah, so basically this was motivated by a theorem of Mutra-Mustazza, which compares the Bernstein-Sato polynomial of the tuple F1 up to Fr with G, but you have to sort of remove the trivial root. And we strengthened that to some comparison of the V filtration. So here you can prove things, well, I mean, this is really how we show that our definition of the minimal exponent does what you want it. So it classifies higher Dubois and higher rational singularity.